Hello everyone. Today we will discuss about the band theory of solids. Before we start the band theory, we must recall that an atom has different energy levels having fixed energy values for an isolated atom case. But what happens when these atoms come closer to form a crystal? Let's take a teaching aid to understand that. Now if I have a crystal, then all the atoms in that crystal will be identical. I am giving you an example of two atoms to show how this crystal formation occurs. Suppose this is your one atom, this is the other atom. Now if you look at the isolated atom, it has different shells. See, this is the nucleus. This is 1s2, 2s2, 2p6, 3s2 and 3p2 if we are talking about the silicon atom. Because we know that silicon atom has an atomic number 14. So what will be its electronic configuration? Electronic configuration will be 1s2, 2s2, 2p6, 3s2 and 3p2. So suppose this is your silicon crystal, silicon atom. So if this isolated atom is there, then we have these inner shells which are surrounded by 3s2 and 3p2, which is the outer shell actually. So these 4 electrons are the valence electrons. So this is the outermost shell, or you can say how many valence electrons are there? 4 valence electrons, right? So when these isolated silicon atoms come closer, what happens? See, these are very far away. Now these are coming closer, 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 more closer, more closer, more closer. And suppose this is the equilibrium separation in the crystal when the crystal formation occurs, right? So during its motion from far distance, when these were considered as isolated atoms, when these come closer, the interaction between the outer shells starts, right? The inner shells are shielded, or you can say the protected by the outer shells. So that's why there is no much interaction between the inner shells, but the outer shells, that is 3s 3p, interact with each other when the crystal is being formed. So during this approach, the interaction between 3s and 3p starts, and due to this interaction there is a spread of 3s and 3p, that is the outermost shell, or you can say the outermost orbitals, 3s and 3p orbitals, into a band of energies which is called as energy band. Now if I am taking the example of two atoms which are approaching, then we have 3s corresponding to this one, 3s corresponding to this one. So 3s will spread up into two closely spaced energy levels. But what if we have 10 atoms which are coming close? Then we will have 10 3s and 10 3p orbitals. Now what if we have n number of atoms which are approaching together to form a crystal? Then we will have n times of 3s orbitals and n times of 3p, which is very large number. So what will happen, that the demarcation between these will be lost and we will have closely spaced energy levels, which is called as energy band, and which is formed only when the crystal is formed from the isolated atoms, when these isolated atoms are brought closer to each other, right? So that means if we have an isolated atom, then we have different energy levels having different fixed values, that is 1s2, 2s2, 2p6, 3s2 and 3p2 if we are taking the example of silicon. So this is the isolated atom of silicon. This is just an example, right? Now if many silicon atoms are coming closer, what will happen? There will be the interaction between the outer orbitals, and which will result in the spread of energies across a band, that is the closely spaced energy levels, which is called as band, energy band. Now when these energy bands are formed, we'll discuss this in detail. There is no effect on the inner shells. Why? Because these are shielded by outer shells. So this I am talking about when the crystal is formed due to the interaction of the isolated atoms, when these are brought together to form a crystal. Right? So here what happens is that 3s breaks up, or you can say rearranges in the form of a band of energy for valence electrons, which is called as valence band, and one more band which is also closely spaced energy level, which is for the electrons. When they cross this energy gap, these may reach the conduction band and may conduct. So the thing is, we are going to discuss all this in detail. What is valence band, what is conduction band, how these are formed, but at macroscopic level, at you can say the superficial level, we can understand that when the atoms come closer, due to the interaction between the outer shells, closely spaced energy levels form a group which is called as energy band. So first we will write down the definition of energy band. It is a group of closely spaced energy levels when a crystal is formed from atoms. Now, during the formation of this energy band, we have to understand the complete process, that what happens when these atoms are brought together. That means what happens when the interatomic separation of these atoms is decreased to form a crystal. So let's take the case for different positions. Suppose I am talking about this atom, silicon. So these are very far off right now. In this position, these are very far away from each other. So you can say that these are isolated from each other, act as isolated atoms. So when these are brought closer, this is the second position which we will be discussing, and then when these are brought closer, what will happen? The interaction between the outer shells of these two, that is 3s2 and 3p2, will start taking place, and this will result in the spread of the 3s shell and the 3p shell for both the cases, right? So this is the second position. Third position, these are brought more closer. In this position, there is no gap visible between 3s and 3p, right? So in this position, three s and 3p of n atoms which are coming closer to form a crystal, right? So here I am showing just two atoms, but actually n atoms are coming closer to form a crystal, right? And then after, if the separation is further reduced, and now if the separation is equilibrium separation, so this is what equilibrium separation in a crystal. So I'm talking about the separation when the crystal is formed. So at that time what happens is that the gap appears between the filled shells and the unfilled shells. So that I will explain here in a diagram which will be more clear there. This was just to show the four different separations where we are discussing the upcoming diagram. So first case was this one, when this separation is very large. Then second case, separation reduced. Now here this is the separation more reduced. Now let's discuss that diagram, which is the diagram between the energy and the interatomic separation. So I'm drawing this energy on the y-axis and interatomic separation on x-axis. Now, we know that when the separation between the atoms is very, very large, the atoms behave as isolated atoms. That means there is no interaction between the atoms. Like I had shown this thing, that when we have a very large separation between these atoms, so when this separation is very large, there is no interaction between the two, so these behave independently as isolated atoms, right? So at that time, each atom will have discrete energy values, specific fixed energy values for each of the shells, right? And similarly, the other atoms will also have fixed energy values for every shell which they are having. Now, so if I'm talking about first case when the separation is very, very large, 1s, 2s, 2p, 3s, 3p, and for one atom I'm writing the configuration. Now if I'm talking about n atoms which are coming closer, so for those n atoms of silicon, I'm writing this in tabular form, that for one the configuration is outer shell configuration is 3s2 3p2. What does that mean? This, right? So when it is in the form of crystal, what will be the number of electrons which are there, what will be the empty states, that we are going to compare. So in one atom, in n atoms, and here I am writing 3s, here I am writing 3p, and then I am talking about filled, empty, and here also filled, empty, and this is slightly confusing part, so that's why I'm spending time in drawing this in tabular form, so that there is no confusion in the end. Now look at this. When we have one atom, then how many 3s states are filled? How many possible states of 3s are there for an electron? Two possible states by Pauli's exclusion principle. So these are having opposite spins. So we can say that 2s are filled, two states, you can say two states of 3s, right, are filled. And how many states of 3s are empty? Are there any empty for 3s? No. So you can say nothing is empty. If I am talking about n atoms of silicon, so for one atom, two states were there which are filled for 3s. For n atoms, it will be 2n which are filled. Empty, again nothing is empty for 3s. If I am talking about one atom of silicon and 3p state, so 3p may how many are filled? Two states are filled, right? And how many are empty? 1, 2, 3, 4. So 4 are empty, right? Similarly, for n atoms, if two are filled for one atom, then 2n are filled for n atoms and 4n are empty. So you can say how many electrons in 3s for one atom. So it will have 2 electrons for one atom. But for n atoms, for 3s states, how many electrons will be there? 2n electrons will be there. Similarly, for 3p, for one atom of silicon, it will have 2 electrons, but for n atoms, it will have 2n electrons. Right? But how many electrons can be accommodated for one silicon atom? 4 can be accommodated from somewhere else because 4 are empty in 3p state. Now for n atoms which are coming closer to form a crystal, 4n electrons can be accommodated from somewhere else. Now this n atoms is the case in a crystal, and this is the case in isolated atom case. So when the interatomic separation is very large, then we can say that these behave as separate discrete shells where the energy value is fixed. But when these atoms come closer, so you can say when these atoms are separate, then for 3s we know that 2n are possible states for 3s, right? And 2 are filled. So 2n electrons are there. For 3p, how many states are filled? 2n electrons are filled, right? But total how much is possible? Here the total is actually 4n plus 2n. Total possible is 6n. So you can say 6n possible states are there, but 2n are filled for when n atoms are coming closer to form a crystal. Now when these are coming closer, what is happening is that each of these, due to the overlapping of the outer shells as I had just shown, so due to the overlapping of shells, so if n are there, we know that if we have n atoms coming closer, then each will have 3s, 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 3s interactions, and each will have 3p, 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 3p interactions. So there will be interaction. So each of the electron is having specific value of energy due to specific interaction with the other electrons of the other atoms which are coming closer to form a crystal. So each of the atom is having, each electron which is having a specific interaction with the other atoms and the other electrons of the other atoms. So that's why each of this will divide into how many? 2n number of energy levels, right? So this will start to spread like this. This will be actually 2n. right? Similarly, this 3p will start to divide into 6n. So this spreading is actually 6n energy states. Why so? Because n number of atoms are interacting to form a crystal. So this will have so many interactions that more the interaction, more is the spreading. More is the interaction, more is the spreading, right? So what happens is the energy of some of the 3p reduces, so it becomes lower. Look at this. Now energy of some of the 3s increases. Look at this, the energy is increasing. So due to this position, what happens is at some point there is no clear-cut demarcation between the energies of 3p and 3s. That clear-cut demarcation is not there. So in this time we can't differentiate which one is 3s electron and which one is 3p electron. So this separation, or you can say the gap between the energy, is lost because of more spreading of 3p and 3s due to more interaction between n number of atoms. So at this point, this is mixing, no clear-cut demarcation. So this point corresponds to the third, that is more reduced separation case. This point corresponds to, when the spreading occurs, this point corresponds to reduced separation, and this one is like isolated atom case. Now after this, if further the separation is reduced, you know that this is 0 over here and this is the interatomic separation. So if the separation is further reduced, so what happens is, we know that there is no demarcation, there is no gap between 3s and 3p. So what will happen if higher energy electrons, right, they get a chance to mix up with 3s. So there is a mixing of s and p orbitals, which is the hybridization concept which you have studied in chemistry. Now due to this opportunity to the electrons to fall into lower energy state, we know that in nature, for equilibrium to be possible, the energy must be minimum. So these electrons tend to shift this side towards 3s side to have lowest energy. So what happens is, due to this further decrease in interatomic separation results in shifting of electrons here. So all the electrons will be here and this will be empty. So now the bands which are formed here, this band is called the conduction band, and this band is called the valence band. So you can say that all electrons are here, right? So what is actually the case that in this case all the valence electrons shift to the valence band and all the other shells remain empty, and the energy gap between these is called as energy gap only, or forbidden energy gap, where no electrons are there. So there is no electron possible in this energy gap. So let me sum up all the things all together. So when the atoms are isolated, then these have discrete energy levels. When these atoms come closer, as the separation decreases, the interaction is more and more, and as the separation decreases, there is a spreading of 3s and 3p into many energy levels. More is the interaction between the atoms, more is the spreading of this 3p and 3s. And then if we reduce the separation further, the energy of some 3p energy levels reduces, and energy of some 3s increases, due to which there is no distinct separation between 3s and 3p. Now in this case, when the electrons in 3p get a chance to fall into lower energy state, so at that time all these electrons from 3p, these shift, or you can say, you can't say it separately 3p, all the electrons from here shift to one place, which is lower energy state, because lower energy state corresponds to equilibrium. So this place where all the electrons are gathered, this is called as valence band. So this group of closely spaced energy levels where only the valence electrons are there, this is called as valence band. Now all the empty shells or empty energy levels are together called as conduction band. The energy gap which separates the valence band and the conduction band is called as forbidden energy gap. So this way, if we see, we have two bands. One is valence band, right? So here we can write important thing. Valence band, it has valence electrons, right? Second thing, it is partially or completely filled, right? Third is, these are bonded electrons, therefore can't conduct electricity. And what is valence band? Actually, we can write this definition also here in short. It is a group or band of closely spaced energy levels having valence electrons. Then we can write the conduction band. The band which lies above the valence band the free electrons reach here after getting energy equal to energy gap, right? So here empty at 0 Kelvin and partially filled at higher temperatures. So conduction band has conduction electrons. Actually, when the electrons reach the conduction band after getting energy equal to energy gap, right, then these can conduct. So let me read out this for you. The writing is very small over here. Conduction band conducts electricity due to conduction electrons when electrons from valence band reach here on gaining energy equal to energy gap, right? So this was all about the band theory and the concept of valence band and the conduction band, right? So that's all for now. Have a nice day.